Hey, happy physics students. Have I got a treat for you? We are going to delve into the velocity versus time graphs. In the last video, we talked about position versus time graphs. So, in position time graphs, just as a quick review, you had a graph where you were plotting the position data and the time data. And by the way, some people, plot distance or displacement on this axis. The whole point is that you're trying to locate where something is in meters and in seconds for the time, and you get different shapes. So we talked about how constant speed is a straight line. This is moving right, this is moving left. So left, right, and then you can have speeding up. So speeding up to the right would be something like this. Speeding up to the right. And speeding up to the left would be something like this. And let's see. Why is that? Because the slopes are increasing. We talked about that in the last video. And then what about slowing down? What would that look like? I'm just going to extend this axis to continue example. Because we talked about it really doesn't matter where you start, what your starting location is. It's really just the shape of the graph that's telling you how it's changing and how you're moving. So speeding up, slowing down, and in what direction. So let's talk about slowing down so my graph has to increase and my slopes have to get smaller, so it'll look slowing down to the right, like that, a bowl down shape. And slowing down to the left would mean my slope would start steep and get flatter, so this will be slowing down to the left. In this video, we're going to talk about a very different kind of graph that is about velocity versus time. So it's telling you, and it's giving you information about how fast something is going at a given time. Okay, so if I just sketch this graph, let's say I have a crazy graph like this, bam, who cares? And I just read it. Let me put some numbers here, because I don't know what I'm talking about until I put some numbers. I'm just learning how to do this stuff. I'm just going to read this graph. So at 1 second, it looks like I'm moving at a speed of a little over 1 here. Let's call it 1.3. So right here is 1.3 meters per second. So at 1 second, I'm going yay fast. All right. Then let's read something else here. At 3 seconds, how fast am I going? It looks like, let's call it 6-ish meters per second. All right. Now this is a velocity. It's a vector. So signs matter. So all of these numbers are positive, right? Because I'm reading positive velocities. So basically, this entire graph shows that something is, having different speeds at different times. So it's clearly not moving at a constant speed. And it's also always moving to the right, because all of these numbers, the velocity numbers, are going to be positive. So this graph is showing motion to the right, and it's definitely changing its speed. Sometimes it's speeding up, sometimes it's slowing down a little bit, and it has little dips and valleys. All right. So on the flip side, let's say I have something like this. Again, let me draw a crazy graph, but don't freak out. It's just a graph. Bigger things in life than graphs. So I'm below the zero here. Again, I'm just going to read the graph, because that's going to help me figure out what the heck I'm doing. Again, this is time here in seconds. And so let's see what's happening at 1 second. If I go down to the graph, I read it. It's like negative 1.6-ish, I don't know, meters per second. So what it's saying is I'm moving 1.6 meters per second to the left, because we've set it up like that in this course, that negative, south, left are all the same thing. So again, you're reading speed numbers here and directions. Here you are reading where something is, or locations. They're two very different graphs Before you launch into your analysis of a graph, please read what the heck is being plotted on it. All right, so at 3 seconds, again, I'm going to read the graph. Looks like it's a little bit here, so that's negative 1.2-ish, I don't know. So it looks like my speed number actually, see what happened is I actually slowed down because my number is smaller than 1.6. So my rate of movement is slower. But I'm still moving to the left because this is a negative number. In any case, now let's sum it up. So this entire graph is showing you motion to the left. And again, you're changing your speed. So just remember that on velocity time graphs, the signs are telling you direction. So I'm just going to sum it up here. The signs tell you direction. And the values are telling you the speed, right? So if you break it up like that, you'll know how to tell the difference between fast and slow. I mean, you just read it off the graph. Here you have to find slopes of fast and slow, remember? Like this would be faster than, for example, this, because this is a steeper slope than this, and you would have had to calculate that slope to figure out the speed. Here you just read it off the graph because it's telling it to you in meters per second for each value. And the sign tells you whether you're moving right or left. All right, so let's connect this to something like a free fall problem where, let's say you throw a ball up at a velocity of 30 meters per second initially. Remember, we label initial velocity VI, and some people call it VO. I don't know, V original, V at 0 seconds, whatever. They mean the same thing. You start off, and then that's at 0 seconds, right? Now, I know that gravity is going to be slowing things down in the free fall model. Acceleration is kind of known in all the problems. You're assuming it's approximately negative 10 meters per second every second. So what does that mean, negative? Let's break that down. You have a positive velocity if we define up as being positive, right? So we talked about in class how when you have a velocity pointing one way and an acceleration pointing the opposite way, that you have slowing down. So we labeled acceleration negative here because we know when you throw something up, it's going to slow down, which means that if that way is positive, A has to be negative. It's working against the velocity. You can think of it as subtracting speed away every second. So every 1 second in this case, it's subtracting away a speed of 10 meters per second. So each second, it's going to drop its speed by 10. And usually acceleration is written like this. Right, we talked about in class how these units really make those units, and people are like, oh my gosh, why don't the seconds cancel? I don't know. Well, let's see. You got a fraction, and then you got another fraction on the bottom, seconds, but it's like seconds over 1. Like if you have a whole number, it's really the whole number over 1. So when you divide fraction, you take the toppy thing, you just move it here. And then you take the bottom thingy and you take the inverse of it and multiply it by the top by the inverse. So it's 1 over second. And lo and behold, what you get is you multiply the tops, meters over second times second makes second squared. Ta-da! There's your units for acceleration. Now, all those people who are going to yell at me because I just gave you a simple algorithm for dividing fractions instead of explaining it, we talk about in class for those people who don't understand how to divide fractions and break that down. That's like 4th grade math. So I'm not going to do that here. Anyways, so getting back to this problem, if gravity is taking away 10 meters each second, I'm going to draw where it is at the next second. And its speed has dropped by 10, so now it's going to be plus 20 meters per second. All right, after another second, it's still slowing down. It doesn't go as far each time, so the distance is decreasing, right? Between this second, it goes further than during this second. So here I have at 2 seconds, dropped by another 10, that's 10 meters per second. And then during the last second, I'm going to have to decrease my distance even more. Okay, here we go. At the third second, it took away all the 10. That's why I picked this nice little number, just to show you the concept that for an instant, at the top, its speed is 0 meters per second. All right, basically I've just explained to you what acceleration means, that it's a change in velocity. So in this case, it's a slowing down effect because it's opposite the velocity. You represent it by a vector that points against the velocity to show the slowing down. But we know things don't just get up to the top and hover. Okay, we know that. So at the fourth second, what you see is in fact it doubling back. I'm drawing it on the side, but pretend it's just going straight down. If I drew everything straight down, you'd be totally confused by the mess I would make on this paper. So I'm drawing it on the side, so at 4 seconds, what's happening is now, look, the velocity flipped directions, right? So it's not positive anymore. It's now going down. It's negative. And in this case, the acceleration is actually going to be working with the velocity, and you're going to see a speeding up effect. So at 4 seconds, it's going to gain 10 meters per second, and the velocity is negative. So it's going to be gaining velocity in negative direction. And then here, it's going to gain 10 more. It's going to be negative 20. That's at 5 seconds. And here, notice I'm drawing them at the same level because literally, when you neglect resistance and air resistance in free fall, it's going to take the same time to go up as it does to come down. And at each level, you're going to attain exactly the same speed at that instant. So here you have again the negative 30 meters per second at 6 seconds. With a simple picture and some logic, I just figured out that if I throw something 30 meters per second up in the air, it's only going to take 3 seconds for it to reach maximum height, at which the velocity is 0. And for an instant, mind you, which is a crazy concept. And then it's going to take another 3 seconds to come back down, and it's going to be basically gaining all of the speed back that it lost when it's at the same level as where you threw it. And so the total trip is going to take 6 seconds. All right, well, why did I do all this? Because now I want to show you what that looks like on a graph, on a velocity time graph. So velocity time graphs, see positive and negative now mean direction. So I got to be really careful here. So each second, 1, 2, 3, 4, 5, 6, 10, 20, 30, negative 10, negative 20, negative 30. And you can fill in the rest because I am lazy or efficient, as whatever you want to call it. So at 0 seconds, I'm at 30 meters per second. Remember, this is my speed now, not my position. And at 1 second, I am at 20. At 2 seconds, I'm at 10. You should always talk to yourself when you plot graphs. It makes them more accurate and you enjoy yourself a lot more. And then at 4 seconds, so this is 1, 2, 3, 4, 5, 6, psi, negative 10, 4, negative 25, negative, freehanding this graph. You see I'm about to get a straight line. Okay, so, what's going on here? Well, what I basically drew is here it's going up. Up is the same as right, positive. So that's this part of the journey. And then we have this instantaneous velocity of 0, which doesn't last at all. That's what instantaneous means. And again, I said that's a crazy concept. You talk about that when you get to calculus. And then what's happening is the numbers are going to start getting bigger, right? If I forget about that there's a minus sign here, the numbers are 10, 20, 30. So 10, 20, 30, that means faster. So when you move away from 0, you're getting faster, right? So here we move away from 0, you are faster. And when you're on the positive side of the graph, or a positive half of the graph, you're moving up in this case, because that's where we define positive. It could be also right. And when you're below 0, you're moving in a negative direction, and you're moving left. Also, if, let's say, you had a sideways problem. Notice another thing here is that what does the slope of this graph mean? So the slope on a velocity time graph, well, it's calculated. Rise over run. Bam. So we have a rise of, what is this, 30 meters per second. And then you have a run of 3 seconds, right? Because here's my little triangle. So rise over run, 30 meters per second over 3 seconds. And remember this, you're dropping. You're not really rising, you're falling. It's more like fall over run. So it's a negative slope. And when I do it out, I get negative 10 meters per second squared. Now, for the people who are sticklers for the fact that acceleration due to gravity is 9.8, even the AP is now using just 10 because nobody cares if you can use your calculator to work with decimal numbers. Everyone just cares if you understand the concepts. So I know that acceleration gravity is not really 10, and it's also not 9.8 at every location on the Earth because of the mass and density underneath. But nevertheless, that's what we use for most of our problems because the concepts themselves are hard enough for most students. So let's go back and review this. On a velocity time graph, plus any point in the plus part means you're moving up or to the right. Any point in the minus part means that you're means that you're moving to the left or down, as in this case. And a slope represents acceleration. So if you have a constant slope, that means the acceleration is constant. It's the same. There was always a 10 meter per second every second being either taken away or added on to the speed. The change, see, acceleration, we talked about this in class, is the change in velocity per unit time. And we spend a lot of time on this delta thingy, which is basically subtraction. So you're subtracting initial and final velocity. So you're looking at the difference each time. And the difference between here and here was 10. That's what it is, negative 10. And the difference between here and here was negative 10. Why are the dots farther apart here than here? Because you're moving faster. So on average, you've covered this second in a lot faster way than here because you could move farther in that second. So for those of you who now want to interpret a velocity time graph, here let me try to draw something crazy so we can talk about it. I don't know, let's do this, this, let's do that, let's do that, and that. Okay, I don't know, that's what came out. So let's call this time interval x, y, we don't care how many seconds it really lasts, z, x, y, z. Let's put w here, we missed him somehow. And let's talk about this section of the graph and call him, I don't know, b? Sure. Circle back, wrap around to the starting letters. So what's happening here? Again, hard to think without numbers. So I look at my axis, bang, velocity. Okay, measuring values in meters per second. If I'm in SI units, let's say, sort of slap some numbers on the graph: 5, 10, 15, -5, -10, -15. People love giving you graphs with no numbers on the axis because they want you to reason abstractly. But if you're having trouble, might as well put the numbers on there until you're comfortable. So if I read the numbers, the speed here at half a second is a +5 meters per second, right? And here it's a +10. So clearly I've been moving faster. I went from 5 to 10. And I've been moving to the right because these numbers are all positive. These numbers are all negative. So here I'm moving right. Please don't say accelerating right. Please don't say going right on acceleration, because just associate moving right with velocity and displacement. That's what moving right means, in a positive direction. And it's a constant slope, so it is speeding up, right? The numbers are getting bigger, speeding up with constant acceleration. Okay, so that's what slope means here, right? Remember, rise over run. Here's the 10. This is my rise. My run is 1. This is meters per second. This is meters. 10 over 1 is going to be a slope of 10 meters per second squared. Okay, so I somehow ended up with free fall here again. But you can make things accelerate this much and not be in free fall. You can use other forces to do that. So nothing sacred about 10 meters per second just associating itself with free fall. All right, again, here what's going on. What's a flat line mean? Well, if I read values during this time, oh, I'm moving 10 meters per second. I'm moving 10 meters per second. I'm moving 10 meters per second. Okay, so am I changing my speed? I don't think so. Again, I'm moving right. And I am moving at constant velocity. So I can even write that acceleration is 0 here, right? Because there's no acceleration. I'm not speeding up or slowing down or changing direction. Okay, let's take a look here. My numbers are getting smaller. Numbers mean speed. So I am here slowing down. And you can see I'm slowing down because I started at 10 with my made up numbers and I ended up at 0 where you cross the axis. So I had an instantaneous stop. I'm slowing down and I am moving right. And here I was moving right as well because my velocity was positive. Okay, here I am transferring over from positives to negative values, right? A negative velocity means moving left. So this is like a turnaround point. Anytime you see a 0 on a velocity time graph, that's a turnaround. Turn around. What's happening here? Well, now I'm moving away from the axis. Again, forget the negatives. Look at the values, 5, 10, 15. They mean speed. So you are speeding up because the numbers are getting bigger. And the numbers are negative, so you're moving left. And you're not speeding up at a constant rate again because it's not a straight line. So you can only really in this course calculate accelerations where you have straight lines because you can get slopes of straight lines from velocity time graphs. In this case, you're speeding up, moving left, but the slopes are not the same. It's a curvy graph. Again, you have to wait till calculus to do that stuff. I bet you can't wait. All right, so you're speeding up, moving left. Again, here, let's look what's going on. This is a bunch of things going on here. So, first of all, my graph is approaching 0. So my numbers are going to go from 15-ish to 0. So I am definitely dropping in speed, slowing down. But now I look at the signs and they're negative, so I was moving left. And then I stop and turn around, right? It's another turnaround point here. Because I reach a zero velocity for an instant. And then my numbers are going to get big again in the positive direction. So here what's going on is I'm speeding up, going, moving right. Okay. So this gives you a way to think about what's going on with the motion. I mean, another way is with dot diagrams. So during this time, basically, I am gaining speed, so it would look like this, where my spacings will get farther apart. So this is x. Then I kind of stay at a constant speed, so whatever spacing I reached, I don't know, I'm just going to have equally spaced dots during this time because I'm moving at a constant velocity, moving right. So I'm moving right now. Here I'm slowing down, not at a constant rate. Again, it's really hard to show that with dots, but I'm going to try. So here I slow down to 0, let's say. I don't know. Right there is where Z ends. And then I turn around and I speed up. I don't know if these accelerations are the same, but I'm going to double back and go backwards. Let's call this part, now I'm moving left in a negative direction. This part is W. And here it looks like I'm slowing down and still moving left, so I'm going that way, slowing down. So I might decrease my spacings. That's slowing down. I come to a brief halt. I'm not done with my B interval. Shouldn't have done that. Because now looks like I reach a 0 speed and then I turn around to the right again and speed up at a constant rate. Blammo. Okay, so this whole thing here where I kind of turned around, I was going that way, and then I'm going that way. This is left, this is right, left, right. So I slowed down to 0, turned around, sped up to the right. So this whole thing's my B. Okay, just to show you with dot diagrams what's going on in this graph, I think that's helpful to think about motion in many different ways, including graphs, dot diagrams, vectors. If you notice, I threw in the fact that the lengths represent how fast you're moving in this case because it's a velocity vector. If it's shorter, it's slower. If it's faster, it's longer. And the direction, obviously, of the arrow tells you whether you're moving left and right. So just to review, for velocity time graphs, you really have to pay attention to what's positive and what's negative because that's direction. In the previous video, we talked about position time graphs, and there, left and right just meant, if you're going right, well, these are all left. Hold on. If you're moving left, your position numbers are decreasing. That's very different than here, where if you're moving left, your values of speed are negative. And if you're moving right, let's see if I can quickly find moving right graphs. Here's some examples of moving right graphs. You can see the position numbers are increasing, but the slopes are different if you're speeding up versus slowing down. Again, moving right on the velocity time graph has nothing to do with slopes. Instead, it has to do with sign. And speeding up, slowing down really has to do with the values you're reading on the graph. Are the numbers getting bigger or are getting smaller? That's about speeding up, slowing down. Here the numbers are getting bigger, smaller, and then you look at the sign and decide whether it's left or right. So, two different sets of graphs, two different meanings. Slope on a velocity time graph means acceleration. Slope on a position time graph means speed, right? Speed and direction. So here we talked about in free fall, um, or any kind of problem where you're going to the left or downward, the slope is telling you the velocity. So you're going down or left here, and the value of the slope, rise over run, will tell you how fast, because it's going to be in meters per second, right? Y's over x's. Here, your slopes are in meters per second, which means acceleration. So go back to your homework problems, take a look at the graphs, see if you can interpret them yourself, and good luck.